All right, friends, we are marching on our way. Sorry, got to interrupt for the moment. We are marching on our way through infinite series. We are taking a look at infinite series and whether or not they converge to a value or they diverge somehow, maybe to infinity, maybe because they oscillate. And one of the big tests we have that will help us see if a series converges is the integral test. That is the topic of this screencast. And the integral test uses stuff we already know how to do. Mathematicians are really good at taking things that we know how to do and using them in other areas. Oh, that's not true. So let the sequence A sub n be a sequence of positive terms. Suppose that each A sub n is a function of n for some positive, continuous, decreasing function f. In other words, if we were to take the values of n and plot the A sub n's, A1, A2, A3, A4, A5, A6, A7, and so on. If the function that connects them, if a function that connects them is positive, continuous, and decreasing, then the series start at 1, go to infinity of the A sub n's, and the integral from 1 to infinity of f of x dx both converge or both diverge. And this is a super important idea. If it is possible to connect these dots with some function that is positive, continuous, and decreasing, then if we were to figure out the integral, the area underneath the curve from 1 to infinity, well, how does that work? Well, the integral from 1 to infinity is basically adding up a whole bunch of rectangles. If you add up the whole bunch of rectangles and that converges, well, then adding up a bunch of rectangles must also converge. If you add up all the rectangles and that diverges to infinity, then adding up a bunch of rectangles must also diverge to infinity. The warning here is important. Warning, 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 warning. It is not necessarily true that the green sum and the red integral will be the same value. In fact, I don't really know of a situation where that is true. If the integral converges, then the series converges, but not to the integral value. Okay? Time to play everybody's favorite game. Does it converge? It's a great theme song. Love the theme song. Does it converge? Shouldn't put an equal sign there because we don't care about an equal sign. I want to know, does this series converge? Okay, fine. I'll write out a few terms. I'll put an equal sign. This is the series in question. I want to know, does that series converge? And I have no reason to believe that it doesn't, but I have no reason to believe that it does. This is not a geometric series. There's no no real good pattern to grab a hold of. So I'm sort of wondering, well, what do I do with that? Uh, so, so what do we do with that? Well, we consider the integral from 1 to infinity of 1 over x squared dx. And we know what that is. It's the limit as b goes to infinity of the integral from 1 to b. Well, what's the antiderivative of x to the negative 2? That's x to the negative 1 divided by negative 1. And so this turns out to be, okay, so this gets subbed in. You got a negative 1 over b. B goes to infinity. That's 0. Subtract what you get when you throw 1 in there. You get 1. Because this integral converges, this sum converges. Now, we should note, this sum, this series, does not converge to 1. Obviously, this series is clearly bigger than 1. But because this integral has a sum, this series has a sum. Okay? Okay. Your turn. I'll wait. I'll wait, but not too long, so you might want to hit the pause button on this one. That's right, friends. Boy, is this a doozy. Right? Since this integral is infinitely large, this sum is infinitely large. And you're thinking to yourself, wait a second. I'm adding up things that are getting smaller and smaller and smaller till they're practically 0. I add them all up and I get infinity. Right. But wait a second, coach. I'm adding up a whole bunch of things that are getting smaller and smaller. They're all positive. They're all getting closer to 0. But I add up these zeros and I get a number. And I add up these zeros and I get infinity. Yes. That is exactly right. You have got to be kidding me. And yes, I am. I am dead serious. I am dead serious. These are examples. Infinity's weird. I keep trying to tell you. Infinity is weird. These are examples of p-series. They are series of the form 1 over n to the p. These series converge if and only if p is bigger than 1. We handled the case where p is 1. If p is bigger than 1, you should walk through what the antiderivative of this thing would look like. If p is bigger than 1, and then you should consider what the antiderivative of this thing looks like if p is less than 1. This is the kind of thing that we probably ought to talk about as a group when we get together. Okay, these are p series. Anytime you see a series of the form 1 over n to the p, all you have to do is take a look at the p and ask yourself, is p bigger than 1? If p is bigger than 1, then this must converge, and if p is less than 1, then this does not. Okay, time for a couple more with me. And then you get a couple, and then we're done. Sum, n goes from 1 to infinity, of n over n squared plus 1 squared, and sum, n goes from 1 to infinity, of 1 over n squared plus 1. I'd like to use the integral test. To use the integral test, I have to consider the integral from 1 to infinity of x over x squared plus 1 squared dx. This integral is doable by, think about it, right, right? This is the integral of, let's see, x dx is du over 2. Suck that right out of there. Suck the over 2 right out of there. And this is u squared. So from where to where, if x is 1, u is 2, and if x is infinity, u is infinity squared plus 1. And it can be shown without too much trouble that this is 1/4. And since this integral is a number, this sum is a number. Coming over here, how do I find this antiderivative? What do I do with this? Well, there's two schools of thought. One is that we could do a trig sub, but that's probably not going to happen because you're sitting in your dorm room or in Starbucks or whatever, and you're like, screw you, I'm not doing a trig sub. Forget that. So instead, let's just consider that we already know what the antiderivative here is. That's inverse tan of x. So what happens with that? We get the inverse tan of infinity. Well, what happens to the inverse tan graph as x gets large? It gets closer and closer to pi over 2. And we already know the angle whose tangent is 1. That's pi over 4. So I get a number. And since I get a number, this integral converges, so this sum also converges. Mind you, I have no idea what that sum is, and I have no idea what that sum is, but I know that there is a sum. Time for you to give a couple a try. I want to know, do they converge? The summation from 1 to infinity of 1 over radical n plus 4, and the summation as n goes from 1 to infinity of n times e to the negative n squared. Off you go. 13 minutes. That's not bad. See you soon.